This is episode 7, Magic of Prime under Mathematics Universe. In this episode, we're going to discuss about how to generate all the prime numbers from 2 to a certain n. And we have a very famous algorithm called the Sieve of Eratosthenes. And we're going to discuss about that particular algorithm. Let's start by taking an example. And the example that I'm going to take is n equal to 30. If n is 30, using sieve of Eratosthenes, we have to generate all the prime numbers from 2 to 30. For that, step number 1 is, let us take a list of all the values right from 2 to 30. So we have taken all the values right from 2 to 30. In sieve of Eratosthenes, we are going to concentrate on two important processes. First is called as selection and the second one is called as elimination. We will do one selection, then for that one selection we will eliminate few values, then again we will select another value, we will eliminate few values, select, eliminate, select, eliminate. So eliminate is directly dependent on selection. So if you select, then you can eliminate. Without selecting, you cannot eliminate. And let's discuss about what we are going to select, what we are going to eliminate. Let's see about it. The first selection is going to be the very first value 2. So 2 is the first value that we are selecting. After selecting 2, then we have to eliminate. We have to perform elimination. What we are going to eliminate? We are going to eliminate all the multiples of 2. That is all the multiples of the selected value. So the selected value is 2 and we are going to eliminate all the multiples of 2. And why are we eliminating all the multiples of 2? I am eliminating 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Just eliminated all the multiples of 2. Why? Because for 4, 6, 8, 10, 12, for all these numbers, apart from 1 and itself, 2 is a factor. 2 is a factor. If 4, 6, 8, 10, all of them are multiples of 2, then which means 2 is a factor of all those numbers. And if 2 is a factor of all those numbers, and apart from 1 and itself, if a number is having another factor, then it cannot be taken as prime numbers. So all these numbers cannot be prime numbers. So let's continue in the same fashion. So one selection and a set of elimination is over. Now let's get into the next selection. So the next value that we are going to select is the next immediate value 3. After selecting 3, we have to eliminate all the multiples of 3. So which means 6, 9, 12, 15, 18, 21, 24, 27, all the multiples of 3 has been eliminated. But if you very carefully listen, when we selected 2, we started our elimination from 4. When we select 3, we have to start our elimination from 6, but 6 was already eliminated because of multiple of 2. So where our first elimination is then? We started eliminating 9. That was our first elimination. 6 has to be the first, but we eliminated 9 because 6 has already been eliminated because of 2. So if we select 2, we start eliminating from 4. But if we select 3, we start eliminating from 9. Okay, let's proceed further. So what is the next value that we can select? The next value after 3 is 4, but 4 is already eliminated. So we can select only the values which are not eliminated. So we cannot select 4. So what is the next value? 5, which has not been eliminated. So which means we can select it. So the next value that we have selected is 5. What we have to eliminate? All the multiples of 5. So if you look at the first multiple of 5, 10, which is already eliminated. Next one, 15 is also already eliminated. 20 is also already eliminated. But coming to 25, we are eliminating it now. So when we are selecting 5, I think the first value that we are eliminating is 25. Then 30 is also eliminated. So can you just observe this and tell me, if we select 2, we start our elimination from 4. If we select 3, we start our elimination from 9. If we select 5, then we start our elimination from 25. So what is the connection? if we are selecting I think the elimination is starting from I square. That's what we can observe from here. If I is the value that we are selecting, then I square is where the elimination starts. I square is where the elimination starts. Okay, what is going to be the next value to be selected? 6 cannot be selected because it is already eliminated, but 7 can be selected. But if it is 7 is selected, where should we start our elimination? So we already have a formula. If you're selecting I, then you eliminate from I square. So if you're selecting from 7, then you try eliminating from 7 square 49. But if you look at 49, which does not exist in the list, which does not exist in the list, which does not exist in the list, 49 is greater than the input we have taken. So whenever you're selecting a particular value, the elimination should start from the square of that value. But if the square of that value exceeds the input, it's a confirmation that you have to stop the entire process. Okay, let's stop the entire process. Why we stopped? Because the selected value square is greater than the input. We stopped. But now you look at the list. There are a lot of values striked out, eliminated. There are a lot of values which are still not striked, which are not still eliminated. Let's circle them. For example, 11, 13, 17, 19, 23, 29. So if you look at all the circled values, they are all prime numbers. Starting with 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, all of them are prime numbers. So this is what Sieve of Eratosthenes means. So in Sieve of Eratosthenes, we select a value and all its multiples are eliminated. And we keep going like this. And after doing this process, if you look at the list, whichever element is not eliminated, they are all prime numbers. Now let's see how the implementation could be done for Sieve of Eratosthenes. First step is, let's take an array. And the size of the array has to be n plus 1, which is input plus 1. For example, if the input is equal to 30, then we are going to take the size of the array to be 31. Why? Because if the input is 30, we need the last index to be 30. If the last index has to be 30, then the size of the array has to be 31. Because we know very well that if the size of the array is 5, then the indices will start from 0 and it will go up to 4. If the size of the array is 20, then the indices will start from 0 and it will go up to 19. So if the last index is 30, then the size has to be 31. So the last index has to be n. So if the last index has to be n, then the size of the array has to be n plus 1. So that's the reason why we are taking n plus 1 to be the size. If the input is n, then the size of the array that we are taking is going to be n plus 1. We will see why we want that 30th index, why we want that nth index. So after taking an array of size n plus 1, we are going to store Boolean values, either true or false. All the indices, let us fill it with true. 0th index and 1th index alone we will go with false. What is the meaning of this array with Boolean values? The meaning of this array is that in this array, if you pick some index and if that index has true, then which means the index is a prime number. If the index has false, then that index is not a prime number. For example, if in index 7, if you find true, then 7 is a prime number. In index 10, if you find false, then 10 is not a prime number. So that is the information that this array is going to give us. And 0 and 1 are not prime numbers. So by default, 0th index and 1th index, we are filling it with false because they are not prime numbers. And all the other values we are assuming, to start with, we are assuming that all the other values are prime numbers. Starting from 2 to 30, we are trying to assume all the values to be prime numbers. So that's why we have taken all the indices as true. So I think now you can clearly understand that why we are taking up to 30th index, why we are going up to n plus 1. because I want to generate all the prime numbers between 2 to 30. So which means I want 30 also to be there. So we want 30 to be the last index. That's where the size is becoming n plus 1. Okay, now selection and elimination has to be performed on this array. How to perform selection and elimination on this array? Where we should start our selection from 2. So which means we will start selecting from 2. So let us do the implementation also side by side. So let me start with writing a for loop integer I which starts from 2. So this loop is for selection, and this loop is saying that the selection is starting from second index. So I is pointing to the index where the selection has to start. So I is equal to 2. Selection starts from second index. Okay, now let's not worry about the condition, and I'll go with the incrementation as I plus plus. So which means we have to visit every index starting from 2, and then we have to check whether that particular index can be selected or not. If it can be selected, then we have to go with the elimination. Okay, let's come into the loop. Now let's assume that if I is equal to 2 and we are entering into this loop, we have to verify whether that index could be selected or not. How can we verify? An index can be selected if it is not eliminated. The index cannot be selected if that particular index is eliminated. Index I can be selected if that index I is not eliminated. That index I cannot be selected if that index I is already eliminated. And how can you determine that an index I is eliminated or not? You go to a specific index. If the index has a value true, then which means that index is not eliminated. But if the same index has the value false, then which means that index is eliminated. So now I need to check whether that ith index is not eliminated. How will we check? If, let me assume that array name is primes, and I'm going to go to ith index and just check this, is prime of I. Suppose if that index has true, which means it is not eliminated. If it is not eliminated, which means we can select that particular index. So this if condition, if it is satisfied, we can confirm that ith index is not eliminated and the ith index can be selected. So entering into the if block, whatever our I value is, that index is selected now. Now, if ith index is selected, that is like if second index is where we start our selection. So if second index is selected, then we should start our elimination from, we have already seen a point that if I is selected, then the elimination starts from I square. That is, if 2 is selected, the elimination starts from 4. If 3 is selected, the elimination starts from 9. If 5 is selected, the elimination starts from 25 and so on. So now I is equal to 2 and the elimination has to start from I square, 2 square 4. So let me write another loop for elimination, because we are not going to eliminate only one value. We will be eliminating a series of value. So let's start with the loop, and I'm going to write j equal to, where is the elimination should start from? If I is the selected index, then I square is where the elimination has to start from. So if 2 is selected, then I square 4 is where the elimination will start. If I is equal to 3, then 3 square 9 is where the elimination starts. That's why we have started with this initialization. And up to, say, if you see, for example, if 2 is being selected, then 2 square 4 will be your first elimination. Then 4 plus 2, 6 is your second elimination. Then 6 plus 2, 8 plus 2, 10 plus 2, 12 plus 2, 14 plus 2, 16, 18, 20, 22, 24, 26, 28, 30. All of them are eliminated, which means, can you see that we are reaching the last index? So there is a possibility that the elimination can go up to the last index. So here I'm writing a condition that j less than or equal to n. The elimination can go up to the last index. And what is going to be the incrementation? we are not going to increment by 1 and waste, because if 2 is what we select, 2 square 4 is where we start our elimination. From there on, can we increment plus 2 to get to 6? Why should I reach 5? I need not to reach 5th index, right? So from 4 directly plus 2 6, from 6 directly plus 2 8, from 8 directly plus 2 10, from 10 directly plus 2 12, and we can keep incrementing it by 2. What if we are selecting 3? If you're selecting 3, then 3 square 9 is where the elimination start. And from there on, if you want all the multiples of 3, then 9 plus 3 12, 12 plus 3 15, 15 plus 3 18. You can find all the multiples of 3 and you can eliminate. Very similarly, if 5 is what you're selecting, then 5 square 25 is where you start your elimination. And from there on, you can increment it by 5 to find all the multiples of 5 and eliminate. So if selected index is 2, increment by 2. If selected index is 3, increment by 3. If selected index is 5, then increment by 5. And the selected index is generally represented as I. So you have to increment this by I every time. First time if I is 2, then this J loop will be incrementing by 2. Then if I is equal to 3, then J will be incrementing by 3. So whatever is your selected indexes, that many times your elimination loop will be incrementing. Now how to eliminate? Very simple. If you make a particular index false, then it is considered to be eliminated. So now, is this loop for elimination? Yes, J loop has been written for eliminating. So getting inside your J loop, go to is primes, go to jth index and just set the value to false. You're eliminating all the J index. So if I is equal to 2, then 2 square, you start here 4, and then it will be loop will be incremented by 2 every time. So first time J is 4, so you go to 4th index and you set it to false. Then plus 2, you go to 6th index, set it to false. Then plus 2, you go to 8th index, set it to false. So you will be setting all the multiples of 2 to false. Similarly, the same happens to multiples of 3, multiples of 5, and all the elimination will be perfectly done. Now we have to speak about the condition that we need to write here. When we will stop our selection, we have already learned something, right? If we are selecting I equal to 2, then the elimination J starts from I square, right? So let me assume that if the selection is 7, which means I equal to 7, then J should be equal to 7 multiplied by 7, 49. So if the selected index is 7, then the elimination has to start from 49. But look at our input. Our input is 30, and this 49 exceeds that 30. This 49 exceeds that 30. So which means that you are not going to eliminate any new values when you are selecting 7. So when you are selecting I, check whether your I square, I multiplied by I, is less than or equal to your input. If that's the case, you continue. But if your I square is exceeding your n value, stop, which means there cannot be more elimination. Every value that needs to be eliminated has already been eliminated. Nothing new to eliminate. So which means we can stop the entire selection process also. So here we have to write, after selecting I, let's check whether our I square is less than or equal to n. I multiplied by I less than or equal to n. Then you proceed. If that condition is false, then stop. So this is how the entire implementation has to take place. And with that, let's jump into the implementation. Let's start with the implementation. And to start with, let us first of all receive the input integer n. If n is 30, then we have to generate all the prime numbers from 2 to 30. Okay. Then we will receive the input for this n. So Cn double greater than n. So we have received the input for n. Now let's write a function to generate all the prime numbers. So let the name of the function is Sieve, and it is going to take a parameter called as n. So anybody can call this function Sieve and pass any integer value, and if you're passing some n, then all the prime numbers from 2 to n will be generated by sieve, and that set of prime numbers will be returned to us. And those prime numbers will be returned in the form of vector of integers. So we are going to take the return type as vector of type integer. And to use this vector, we need to also include the class vector, so which means I will include vector also here. Now coming into this sieve method, sieve function, step number 1 is we want a Boolean vector. Remember, that is a process that we just discussed. We have to be taking a vector of Boolean, and let us take the name of that to be is underscore primes, and let's take the size of it as n plus 1. And we also should be setting the default value to true for every indices, but just for 0th index and 1th index, we can set the value to false. So 0th index and 1th index, both the indices are going to be false, which means that they are not prime numbers by default. We know that. And after this, we have to start our selection, and the selection starts from 2. And we have already seen that whatever we are selecting, if you are selecting I, then the elimination has to start from I square. And if that I square, I multiplied by I, is less than or equal to the input, we can continue our selection. And every index I has to be checked for selection. And coming into this loop, we cannot take all I to be. We cannot select all I. Every I cannot be selected. Ith index, which is not eliminated, can only be selected. So we have to check for that condition. If is underscore primes of I. So if any ith index we are picking has true in that particular index, then it is not eliminated. So if is primes of I is having true, then which means I can be selected, ith index can be selected. If ith index can be selected, then we can start our elimination, and the elimination starts from I square. So integer j equal to I multiplied by I. And the elimination can go up to the last index, so I will run the loop up to n. And we will have to increment this j by I, because whatever is the selected index, you have to find all the multiples of that I, and if you want all the multiples of I, then increment your inner loop by I times. So j loop is incremented by I times to find all the multiples of I, and to eliminate, we will go to that particular jth index and we will set the value to false, eliminated. That's it. Now if this loop is over, certain indices will have true, certain indices will have false. Whichever indices are having true, they are all prime numbers. And let's take all those indices out. Let's filter them. For that, let me take one more vector, and this time the vector is going to be of type integer, and let us name that to be primes. No size, no default value. Now let us iterate the entire is primes vector. So how to do that? For integer I equal to 0, then I less than or equal to n. So starting from 0 and going up to nth index, let's visit all the indices I plus plus. And now we have to check that index I. If the index I has true, then I is a prime number. If ith index has false, then I is not a prime number. So let's make a check. If is underscore primes of I, and if this condition is true, then I is a prime. So if I is a prime, let us go to the new vector primes, just push it, and dot push underscore back of I. Just push I into the new vector that we have taken. And now after coming out of this loop, primes vector primes will have all the prime numbers alone, which we can just return from this function. So return primes. And now let's come to main function, and I'll take a vector of type integer, and let me name it as primes here as well, equal to, I will call the function sieve, and I'll pass the input n. So when the sieve function is called and the input is passed, that function, sieve function, will generate all the prime numbers and store it in a vector, and that vector will be returned, and that vector is now stored in the variable primes. Now let's display this primes, and to display primes, let me write for integer prime colon primes. So we are taking every individual prime from the primes vector and just display that. So going inside the loop, I'll write cout double less than prime, and after displaying the prime every time, we will just print a space as well. Yes, the implementation is done, and let's just check the execution. So first I'm compiling it, there is no syntactical error, and let's just execute it and let the input be 30, and we are able to see all the prime numbers. And what if I execute again and just give 100? All the prime numbers starting from 2 up to 100 is being generated, displayed also. So this is it for the implementation, and the entire Sieve of Eratosthenes conceptually, implementation wise, we've thoroughly seen it.